Hello and welcome to day 16 of the Advent of Code 2022. Today, we have a tough problem ahead, and I know because I checked the leaderboard before doing the problem, and I saw that the top 100 user participant spent 24 minutes doing the first part and more than 1 hour doing the second part. So today we know we have a tough day ahead. Let's read the statement. I read it half an hour ago, so I can summarize what I got from it. We have a list of valves, which each has a name. Let's see the output, the input, which I didn't see. Okay, so we see that this is not very big. This describes a graph let's copy it here, and let's copy also the example. We will probably work with the example first, and then try to work with the real input. So let's see what this input shows. What we want to do is for line in open 16.example, for example, let's print the line. That's what we get, right? So what we want to have, what we see is that each valve has a rate. So we could even say, let me also open the input. So yeah, every valve is a two-letter string. So one thing we could do is line.replace equal with space. We could print the line again. So we have, what did I do? Line equals this. So now I remove this equals. Let's replace the semicolon with an empty string. So now we have removed the semicolon, and let's replace the comma with an empty string. This is just a simple way of making our life easier. So now if we split this line, we have this. So now we could say row 1 is the first. Let's print it here. So this is row 1. Then there is 0, 1, 2, 3, 4, 5. There's the int of row 5, which is an integer. And then there's row from, we said this is 5, 6, 7, 8, 9, 10. So from 10 until the end, we have parsed this successfully. DDIIBB. So we got all of them. So now what we can have is a flow dictionary and a neighbors dictionary. This would be what we usually call a graph, right? So we could say from, or we could say valve equals, so we could say valve flow names equals this, and we could say flow of valve equals flow and neighbors of valve equals names. And now we could print this flow. We see 0, 13, 2, 0, 13, 2, what we expect. And we could print the neighbors, which is this dictionary. So from AA, we can go to DDIIBB. Okay, let me edit again the input. We have 59 characters. That 59 valves. That is interesting because that means, I mean, in case we need to go to do some optimization, that fits in a 16-bit 64-bit, sorry, integer. I'm getting ahead of myself, but this is something that we might need for the second part. I don't know. Okay, so we want to know what is the most pressure we can release. And what this simulation or this explanation here shows is that you start in valve AA, so we could say, we could have a function. So part one is going to be max, or P1 is max release given 30 minutes. So having 30 minutes left starting from AA. And let me have an empty dictionary here, which might come handy. So what we have is a max release function that has the time left, the current valve, and let's ignore this for now. Maybe we don't even need this for now. Let's ignore it. So how does this simulation work? Well, if you want to open the current valve, you need to spend 2 minutes. So all of valves are being closed. You start in valve AA, but it must be damaged or jammed or something. Its flow rate is 0. So there's no point in opening it. However, you could spend 1 minute moving. So it takes 1 minute to move somewhere else. So let's have initially, or let's say, if time is less or equals 0, we return 0. That's clear. So if we don't have any more time, we cannot release anything else, right? So then if we want to release the current one, so the return value, if we release the current valve, what we would have is time times the flow of the current valve. We might want to call this V, maybe. So this is that if we release this valve right now, it will add all this remaining time the flow. So this is the flow it releases per minute. So multiply by the minutes. This is all the flow it will relieve until the end, right? All the pressure. And then we could do for n in neighbors of valve. So we can. So there's two options. This one is we release and then we move, or we could move directly without releasing. So if we don't release, let's write the scaffold of the code, and then we can improve it. So what we want to do if we move to this neighbor n, what we do is we max release of t minus 2 and ignore. And we want to return red. So let's go through the simulation here. So all of the valves are being closed. You start with valve AA. So here we could know, instead of ignore, we could have which ones are opened. Okay, and initially, this is an empty set. So we can either we open valve V. If we open valve V, what we do is open.add V, sum this value, and then let's say return is 0, and then here we would do return is the max of return and this here plus. So what we're doing here is we are doing the maximum of opening this one, so the flow that we will open in this, and then releasing this. But however, I'm not sure I'm getting it right with the times. So you start at valve AA, but it must be damaged or jammed, blah, blah, blah. However, you could spend 1 minute moving to valve BB and another minute opening it. Doing so would release pressure during the remaining 28 minutes at the flow rate of 13. A total blah, blah, blah. Then you could spend your third minute moving to valve CC and your fourth opening it, providing an additional 26. So if you open valve V, then you move here. Instead of t minus 1, I will have it like t minus 1. So this would be t minus equal 1. Or here we could do we move directly. So and red equals 0. So if we move directly, what we would do is the following. For its neighbor, we move with time 1. If we open it, we have t minus 1 already, and then we do this. So if we start in 0, and we don't do anything because it doesn't make any sense because the rate of the first one is 0. If we start in AA, sorry, what we will do is we move directly. If we move directly, we don't need to sum this. And we will have the max release of t minus 1, which will be when we get to BB. In BB, if we want to open it, we need to apply this. Okay, so here, open dot delete remove B. Let's see if this works. Max. Okay, key error CC. Why there's CC? Opened. Maybe this is, well, this is not necessary. Let's forget about this for 1 second. Okay. Okay, so here we could say print TV. Okay. So what we see is that we can be moving around all of the time. Let's see. And what I think we need to do is we have to do some memoization. So memoization means that if TV opened in mem, then we can use a Python tool for doing this. We could return mem of TV opened. And here what we can do is we assign this return value to this memoization. What does it say? Okay, V opened, we're missing a comma. And V opened, we're missing a comma. And hashable type set. So instead of this, we could do join opened. Something else we could do, if we want, we could so opened, instead of being a set, it could be a string. Well, is it a string? Well, for this example, it might work. So what we want it to be, let's see. TV opened. So opened plus equal V okay, and one more thing we could do is open equals dot join sorted list of opened. Okay. -1. I don't like this -1. Well, but yeah, we have the return here. So are we seeing the same thing many times? Is it true that we're seeing the same thing many times? I don't think the issue is that we need to use a faster programming language, say like C++ or something. I think with Python we should be able to solve it. But one thing that happens with this kind of searches is that we could also be exploring bad solutions when we already know that. So we could also have the best here. So best equals max of red best. Let's print this. Global best. Let's print the best. 604. Let's see what's the solution. Well, the solution is this. That's interesting. So we could apply some kind of A star in which we already know that we are not going to beat this solution. So if, what is the left time? So if, so if max flow equals max of flow dot values. So if max flow times t, so if we open this right now and we used it for the rest of the time, what we don't know is the current flow that we are having here. But if this, could we know the current flow that we have already? I mean, how far we are from the. So if we had here the current flow initially is 0. If we do this here, the current flow will be the current flow, same value. Here the current flow will be current flow plus this. So here I'm going to change the way we do this, and instead of doing this sum here, we're going and returning red, we're going to return the current flow. If the current flow plus this maximum flow that we could obtain is less than the best, and let's have this global best here. If the current flow plus this max flow, we are not going to get to the best anyway, we'll return 0. Okay. That gave a solution very quick, which is wrong, this 1933, but nevertheless, we got very fast to the solution, so that proved to be a pretty good optimization. So let's see what we got wrong, okay? This opened, if we did this, we'd still have the same. Maybe we want to leave it like this. And if red equals best, let's print TV car flow opened. Okay. AA 0, blah, blah, blah. So we start. No valves are open, you move to valve DD. Sorry. So now we need to backtrack what we're doing to see. Let's have another one with it, which is, let's say, history, right? So in the history, this is going to be history t minus 2. Maybe it doesn't seem like we are that far away of where we want to go. So maybe oh. Okay. Okay. Join, sorted, list, opened. Oh, but this is wrong. This is open plus B. Okay, 1404. We're not finding the best. But some time ago, we were getting this, but here we're not adding. Oh, opened is here. We're doing it here. So I don't understand what changed here. What I changed here is that I put t minus 2, but because okay, but we're having the t in two places, in the minus 1 here and here. Okay, so what is the list of history we set, right? So here we would have history dot append v. Here we add history, and here we add history. Okay, and history is an empty list. Okay, so now hist equals an empty list. Print hist. Okay. Hist. Okay, so this is the history, which is huge because we are not removing things from here. So here we would do so this is not right. This would be history dot append n history dot pop. Okay, that's different. Now if best equals red, then we print history and we print best. Okay, so we have this with an empty history, but we find it here. So, see. Okay, the problem is that we're opening the same valve twice, and we cannot open it twice. So, for n if neighbors, we're only going to open valve V if V not in opened. If V not in opened, then we open it. So let's forget about this ordering now. Okay, 1519. That is better. I mean, it's not better, but it's still wrong. But it is different. When are we getting this? Well, we go to CC. We could, instead of history.append this, we could append the T, the N. Instead of this, we could append it here when we are visiting this. So, well, no, maybe not. Yeah, let's append it here. Because we are here. And then let's remove it here after the fact. So, N. We are going to append V. So, and we're going to say whether we opened or not. So, did open. Well, did open we only know after the fact. So, the point is the best solution, which we got to around here, it says in the 29 we get to DD, in the 27 we get to CC. We're in DD. You move to CC. And from CC you move to BB. It's a bit hard to follow. It's a bit hard to follow. So this is releasing 20 of pressure. Then in the end, 30. Would this help if this was 31? Okay, that is weird. We have a higher release if it's 30 than if it is 31, which is very, 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 very weird. So we're not doing this right. So opened, this opened, we could have a opened string, and we have a set. We would do dot join sorted s. So here we do opened string of opened, and this thing we're going to use in different places. And here too. So, no, not here. So opened is going to be a set. And we're going to have it open.add v. And then we're going to remove it. If this works. Okay, 130. We got a different result, which is already weird. But now, at least this is working as expected. So with 31, we get more results than with 30. So here we are again. Let's see again what we're doing. If the time is less or equal to 0, there's nothing we can do. Then we have our best. The global best is useful for cutting the search early. Okay, so this is related to the. This is related to the. This is a kind of A star algorithm. So what we're doing here is we're checking the minute. If the current flow plus t times, well, but this is wrong. This is not what we want to do. This is not what we want to do. Imagine we change this. So this is not what we want to do, because this limitation is not right. Why? Because imagine it's not like we can do this. What we can do in the best case scenario is not that we can open this only once. We could open this every 2 minutes. Imagine we set 2 times this. Let's see if we get a different result. Okay. Oh, sorry. I did this. So we cut the search if this is true. Let's what am I doing? If the current flow is less than blah blah blah, so let's multiply by 2. Okay, now this is different. If we multiply by 3, the search is slower, we're checking more values, but we're probably getting more accurate results. And indeed, it seems like that is the case. So how can we improve this? Well, there we go. We are getting close to it. Let's see if we can get to this 1651. It is exploring. Okay, 1639 still, but this is still not right. So we might still be losing something. So what is the max flow that we could get? So we could say max flow for a list of opened would be the set, and for t, the set of flow.keys minus opened. Let's print this and return 10, whatever. So what we want to do here is if max flow for this t and this opened is less than best, so this is what we have in this set. So, and what we would do here is for we want to sort this sorted where the key is for each valve, lambda for each valve, we return the flow of valve. Let's print this. So this is sorted in a decreasing. So the F, for example, is it true that it is the one that has, okay, no, it is sorted, but in the ascending order. So now it is H is the one that has higher, right? Okay, that is true. So what we can return is for V in this valve, and let's enumerate. So this is IV. We can return T minus I times 2 times flow of V, return red. Okay, this is not good. This is not good because this is not cutting. This is not cutting this enough. So here we have all of this. We are getting stuck at 70. So we're exploring many things because we see that still it is feasible to improve the best score. However, if we know that the best is this, I think this is the maximum that you can get. I mean, if we did this, what would happen? I mean, this is even a higher bound. Yeah, but this is worth nothing. I don't even know. I don't even know what I'm doing. So if we had done this, we had this one which didn't get to the end. I think we'll have to think about, instead of coding, we'll have to think. This is, sometimes you need to do it, you know? Work out the steps to release the most pressure in 30 minutes. What is the most pressure you can release? So let's think about the algorithm we're using again. So what we're doing, let's see if this will help, 31. Because maybe we don't have the simulation right. Yeah, we already. So another way we could do it is, instead of having this this current flow, instead of adding this, we could have, so this is the end condition, right? If we run out of time, this is the current flow we return. We are choosing to sum all of this. So this is given time t, located at valve v, which makes sense, and having opened all of these valves. If we have already explored this option, then opened, str, opened, you know, no need to do this so many times. Open the str. I don't know if this helps at all, but okay, anyway. So what we're doing is, having opened these valves, we do the memoization step. We add this to the history, which we can also ignore. I mean, we don't need it at all. This is just for debugging purposes. But what we do is, either we move directly to this neighbor, something we could see. Okay. I think we can do this. We can break this even better. So the point is, you are in valve V at time t with opened valves opened. Okay, so I'm trying to find if I have been here already, but this is a bit of a weak check. There may be some stronger check. So first of all, if you have already been in valve V at time t, and the flow that you have opened so far is less than what you had done before, then you can quit already, no matter what is opened. So let's have this different. So this is the memory. Let's remove this memory and say, so the max flow in VT equals a dictionary. And I think I'm going to refactor this, and instead of summing all of these flows, I mean, this current flow already works. This is what we have already closed. So what we can do is, if I am opening this flow, let's close this now. So opened, so if TV in max flow blah 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 and max flow blah blah blah, well, in VT or in TV, right, as seen on TV, if this max flow is larger or equal to the current flow, we return. Otherwise, this is equals to the current flow. Okay, is that right? Oh, that was faster than I expected. Okay, I don't know. I think I'm going to just run the input and see what happens. Okay, I definitely didn't expect this, but we got the gold star. Okay, that was completely unexpected. Completely unexpected. That's interesting. This is what happens with dynamic programming. This is called dynamic programming or memoization, or this max flow we're not using anymore. This open S, this is the same as this. Let's simplify this code a little bit. Okay, OS open. Okay, well, there we are. Let's see part 2. We already saw that part 2 is difficult. So let's see. we will be able to refactor this code for sure. I mean, we can remove this too. History. Well, we don't need the history, but let's see the second part before we remove more things. So the question is, with you and an elephant working together for 26 minutes, what is the most pressure you could release? Okay, there's an elephant now. The elephant in the room. You're worried that even with an optimal approach, the pressure release won't be enough. What if you got one of the elephants to help you? It would take you 4 minutes to teach an elephant how to open the right valves in the right order, leaving you with only 26 minutes to actually execute your plan. Would having two of you working together be better? Even if it means having less time, assume that you teach the elephant before opening any valves yourselves, giving you both the same full 26 minutes. Okay. So now this is an interesting case. Now the search space is growing a lot. So I think we do want to simplify this code a little bit before continuing. Otherwise, well, maybe if the code is bad, you know, it may be harder to reason about. Was it this? 2320. Okay. So now return value is the maximum. So we either move directly to its neighbor or we open the valve and then visit each neighbor. Okay, if we don't remove this, of course this is broken, so we need to remove this. T minus equal 1, we open, we close it. Global best, improve, we remove from the history. We could forget about this history. It's pretty difficult to reason about this history anyway. So maybe we can just get okay, history. Okay. So OS this OS, we don't use this OS anymore because the memory we're having is a time t in valve v. Okay, so we're just and the current flow, are we using or not? Returning the current flow. Current flow, of course we're using it. And the opened, are we using it? What are we using it for? Okay, we're using it to keep track of which ones we have already opened, which of course we need. Otherwise we can open twice the same valve. Okay, so now you have we have two guys, right? We have, well, this best. What if this best is 0? Does that work still? Yeah, of course. Maybe it's better to have 1000. Might be better, but we can forget about this. Are we using the max flow? Not anymore. Can we have this together? Yeah. Okay. So now we have simplified this a little bit. We could max flow. We could just rename this. Do we need the global best? Yeah. Okay. So now we return the current, and if we return the current flow, would this work or not? Yeah, but I think it's harder to return a 0. I don't know. So anyway, if TV in max flow TV and the max flow is larger than what we have already found, we return 0. Otherwise, we set this max flow and then we move. We can either move directly or we can open the valve. So now what happens with part 2 where we have an elephant, right? So the elephant, I think what will happen, we're going to move to part 2 now. I think we have to do very much the same. So part 2 is this, but here we have 26. And then I guess in the minute 1, no valves are open, you move to valve II, the elephant moves to valve DD. I guess we both start in AA. So here we have both us and the elephant start in AA. So what do we do here? Well, this is V and E is the elephant, okay? So if the T is 0, return the current flow. Now, will it ever make sense that we both move to the same valve? Maybe yes. It could make sense. It could not make sense that we both open the same valve, but anyway, so given T, V, we could have TVE, TVE, max flow TVE is the current flow, so this makes sense. But then the problem here is that we have some combination of so it is a bit difficult to manage the time here, because if we both move directly, that's easy. If we both open and move, which doesn't make much sense, in fact that we will never do, but you could open one and move the other, or do the opposite, right? So how can we handle this problem of having two different times, right? So we could have two variables, tme, the elephant, and only move one. Okay, what could we do? What could we do? So what we could do here is TV, the elephant, right? If we have these different times, this would be TV, the elephant, TV, the elephant, TV, the elephant. So we have two times now. Okay, so we would do, if TV is larger than the elephant, move V. And if TE is larger than TV, we move E. And if TV equals TE, we can move one, move both. Let's say we move both. So what happens when we move TV and TE? Instead of just moving one or the other, we could have a tuple, right, of times and positions, because then we could swap them and move move one or the opposite. So we could have TA, TB, TA, sorry, A, B, and we could do, if TA is larger than TB, then return max release of TATB. So sorry, TB, TA, BA, curve flow, open. So the idea for this is that we will have TA being the smaller one. So TA is the one we're going to move always. So TA, let's do it in the opposite way. So TA is going to be always larger. So which means that A is the one that we're going to move always. So TA is always going to be larger. If TA is less than or equal to 0, we return the current flow. Okay, so now we have TA, TB, A, B. Let's have a ID, what could we call it? ID underscore is this. ID. So we swap this if necessary to always visit the larger one first. So now what we have to move is we're going, instead of doing all of this, we're going to move always the TA. Okay, so we move A. If we move A for its neighbor of A, we're going to max the max release of TA minus 1, TB, the neighbor, B, current flow, and opened. If we open valve A and then visit its neighbor. If A not in opened, we open A, we visit all the neighbors of A, and then we do TA minus 1. Instead of doing this, this is T. Well, instead of doing this, yeah, we can do that. So it is TA minus 1, TB, the neighbor, B, current flow, blah, 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 of A. We remove A. And then we return the best. Okay, max release opened. So this is 26, 26, AA. Okay, T is not defined because this is TA. I don't know, I'm pretty excited. We already see that this is not working, but it seemed to me that this makes sense. So if red equals best, let's print the best. Well, we are updating it. Okay. 1707. It is growing. I don't know. Maybe we can get to the solution. Okay. We got too far away. We are getting too far away. We're getting carried away. This is too much. So the current flow, blah, blah, blah. So what are we doing wrong? What are we doing wrong? First, let's print this. Or let's print this ID. Or let's print it here. So we are 2, 1, 3, 1. So of course, the TA is always larger, which is good. That makes sense. So let's think again about what we're doing. So we have this idea of the time of the first visitor, the time of the second visitor, the position of the first visitor, and the position of the second visitor, right? If we have seen the max flow that we can find here and the max flow that we have found is larger than this, then we return 0, otherwise we save it. Then we move the A. When moving the A, we do the max release of the times A minus 1 time B, the new neighbor B. So we have moved A by not B, but not B. So we always move the first one. We always move the A, and here is when we are swapping this if needed, right? Then we move the A, and moving the A means if A not in opened, we add the A, decrease the time of A, and for each neighbor, we try to release, or let's call this max release 2. Well, this is working, otherwise we got an error. So time A minus 1, time B, and B, current flow plus flow A, opened. Opened, remove. Okay, this makes sense. I don't know, let me see the example. I don't know what we... So minute 1, you move to valve II, the elephant moves to valve DD. What would happen if we set flow best to this? It takes some time, right, to get to this. Well, just no, this is just a matter of when you get the best. It doesn't help the search in any way. So we are going too far away. No valves are open. You move to valve JJ. The elephant moves to valve DD. DD is opened. The elephant opens valve DD. When DD is open, it releases 20 for 24. 295. Oh, wait. Am I reading the input? Yeah, that's the thing. I'm reading the input. So maybe. Okay, too low. Okay, so the problem is that I was reading the input, not the example. So okay. Print P1. Imagine if this had worked. Okay, 1707. So okay, so this was working. The example is working. Oh, so it's a shame that the example is working. Wait. Sorry. Print P2. Okay, yeah, so the example is working. And the input, it is a bit slower. I submitted 295 which is too low. Okay, let me assert P2 needs to be larger than 2951. Okay, that is interesting. So we got the example working, which is good. So maybe we are not very far away from the solution. Maybe the input has something special that we should check. Maybe it has something special. Well, there's many with rate 0, which is interesting. we could simplify this graph a lot, but a lot. Oh, this is very interesting. We could have simplified this graph a lot by calculating the reduced graph. So from EF you can go to, or from somewhere you can go to WT, but the WT has rate 0. So from here, the only thing that makes sense is to go either to here or here. So one thing we could do here is to simplify this graph. In fact, there are only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's only 14. There's only 14 valves that really generate flow. So one clear optimization is to simplify this graph. So get the shortest distance from each valve that is generating to each other valve that is generating. We get the shortest path. And then we do the search. So that is clearly what we should be doing. However, we are so close to the solution that it's a shame that we don't have this yet. So what is wrong here? We get the example right. Less than or equals 0. TA less than or equals 0. If TA less than TB. So if TA is 0, then TB is 0 too, right? I don't know if this is larger or than 0. Does this help at all? I guess not. But it's clear one simplification we could do is this of the graph. So what we should do is first find the shortest path from each valve to each valve, and then we can simplify the search very much. I think I'm going to do it just for the sake of having quicker solutions. Okay, still we got this. So how do we get the shortest path? So the difference of what we're going to do is that we're going to generate a graph. So one way to do this, we want to find the shortest path from each node to each node. Okay, but it's not exactly the shortest path, right? What we want to go is from, we're only interested in the ones that have some kind of rate. So what we could do is the following. So I'm thinking of using the Floyd algorithm because it's very simple to code and it is the shortest path from one to the other. So we could have, let's have the distance is a dictionary. So we would have so let's say nodes equal graph equals valve empty list for v in valve flow or valve vf in flow dot items if for vf in flow dot items if flow is larger than 0. So we're interested in the valves that have print g assert false. Okay, so this is the empty list. So what are the neighbors that we have? So what we want to find is so for a in g, for b in g, print ab. Okay. Okay, these are all the pairs, right? So what we want to find is the distance from all the pairs. One stupid way of doing this. One stupid way of doing this is, so we could say g neighbors of a dot append b distance of a b. So, or d equals distance of AB. If distance is larger than 0, then we append it. And then we have the function of distance from AB, which is the following. This we could do with a BFS because this is just the original graph is a BFS. So what we could do is we could have Q equals a list, while Q steps equals 0, while not Q dot, while len of Q is larger than 0. We return -1 if we don't find it. So while len of Q, what we would do is valve equals Q, or valve steps equals Q dot pop. We have the scene is a set. If v in scene continue, otherwise, so if v equals b, return steps, and what we do is for neighbor and in neighbors of v, we q dot append a tuple of the neighbor steps plus 1. Okay, so there's a, in the append, we never close the tuple. Okay, so this is wrong. Print d -1. Okay, so what are we doing wrong? Oh, because first we need to append a. So a 0. Okay, I did not code this right, I guess. Oh, because here is scene dot add b. Okay. So here we have the graph. If we use the example, what we would have is the following. For example, we go to AA, which I'm not sure I will find it now. So where is AA? Or we could go to EE. So EE has DD at distance 1. So EE is connected to DD at distance 1 and to FF2. So we are here. EE has BB. Oh, but FF we probably don't care because it has flow 0. Okay, so EE has this one here, and then FF, which is connected to GG, which means that GG, which we ignore too. Okay, so I think it looks right. So let's check all the prints that we did here. So now we have this graph. And what this graph does is it simplifies the first part. So assert false we can ignore. We can remove, okay. We can add the assert false here. Stop the execution. So here it is 1651. Okay, so now instead of doing this, what we could do is, instead of removing this time 1, what we could do is for n v in graph v. So we, sorry, here. So the distance it takes to get there, it takes, instead of time 1, it takes time v to get there. And this one is the same. So here we could do, if we are opening it, we could say current flow plus equals this. It is the same, but maybe more clear. So this is just the current flow. So we have increased the current flow, but we have T minus D. I not here. Why do we not have I? So do we have I here somewhere? Am I reading it right here? I. Who says I? In GV. I'm not seeing the I. Here, but we're starting from AA. Okay, no, not neighbors. G, so this is again the same. And the T minus, sorry, D. Key error AA. Okay, so we have the same problem, which is that AA is not in the list. We are starting also from AA. So AA could be the exception that we do add. So we could also have if F or B equals AA. So that we get the wrong solution now. So T minus D, and this is probably T minus D minus 1, because we spent 1 opening the valve. Still wrong. We can put this, this here, just, sorry. This here is just, we did it before, just so we are not sure to change anything else. Still wrong. Oh, but this is the same as before. So we have T minus equal 1 because it applies to both things. 1641. We're getting close, but we are not there yet. So again, this is T minus D minus 1. No. Is it? No. 1641. We're almost there, but something is off. So the A8, well, but the A8 will have a distance of -1 maybe. Let's check this. So A has BB1, 2, 3, 4, 7, 2. So A has B1, D3, which is wrong. So the distance from AA to DD is 1. So maybe we're not... So this graph is wrong for AA. For A and G, so let's print ABD. So this is AAAA0, AADD3. Okay, this is clearly wrong. So if we are in AA, for n in neighbors V, steps plus 1. Print AB steps. Let's say here found. Found AADD3. Print append AB and steps plus 1. So we are here. We could also do this if A equals AA, which would simplify the thing, the output. Okay, so if we are here, append DD1 found AABB1 sorry, but I want this if AA and B equals DD. That is what we want. Append 1, append, found. Okay. Okay. Oh, no, 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 no. No, this is not q.pop. This is q0. We should use a deck or something like that. I don't know if we have pop left. And we should from whatever. Let's say q0 and q. This is completely inefficient. We need to use a deck or something like. Okay, now we get the solution. Okay. So this is working now. We still have some prints to remove. We got the graph. We got the solution. Let's go back to the. So now we should modify the second part to use the same simplified graph, right? So what did we do to use the simplified graph? Well, we moved all of the use of these neighbors. So if this is GA and this is NV, then instead of this is a D. And here, this is G and V. So this is V. Let's go up here. Yeah, this is T minus D, T minus D. So this is going to be different now, in which it will be faster. (1707). Okay, yeah, we got to the solution with 1707. So let's check with the input. It seems it's not that much faster. I hoped it to be a little bit faster, but let's see. 1707. So we did get the solution, the same solution for the example. Remember we submitted 2951 or something like that. So let's see if we get the same solution or we get something different now. And we have fixed somehow the bug, even if we didn't know. Okay, this is different. No, this is too low. This is too low. God damn it. We have improved the code. We have computed this graph, but still we don't get the solution. So this is what we have right now. This is the graph we're working with. It probably makes sense to visit the nodes from closer to farther away, but maybe not so, we don't improve that much. We could also use integers instead of strings to represent the nodes to simplify this. So here we are. We have modified the output, but we still don't know what the solution is. So max release, let's check this a little bit more. So this is 2626 AA 0, a set of opened. So the answer is too low. 1 minute. So what we did is TA minus, if this is TA minus is less than TB, we move it. Oh wait, we have this check, which we didn't have before. I don't know if this is going to change anything. But maybe it does. Maybe yes, maybe no. Still, the program is too slow. I think we should make it faster. I don't know if using integers instead of strings would make it faster. Okay. 2963. We still get the same solution. So this is the maximum of return. Max release TA minus D. Current flow opened. Okay, so now I don't know. I really don't know what the issue is. Because the example is working successfully. So if we come back here, we get the 1707. So the example is working, which makes it harder to find what the problem is. So here we swap TB and TA. If TA is less than or equal to 0, we are done. This is the ID, TA, TB, AB, wherever A and B are. If this ID, we have already seen it, and it is larger than the current flow, we return this. We could also return the current flow, but that, I mean, would be the same. We assign this to the current flow, so we update this memoization dictionary. So we move A. We can move A directly. So red is the maximum of this, right? It's the maximum max release for ND in GA. You know, this is the same. We get the max release of TA minus D, so the distance it takes to move there. TB and the neighbor B, the current flow. So we move A. without opening A. If it is not opened, we open it. So we open A, reduce the time of A, because A took some time to do it. For each neighbor of A, we do the maximum. So return is the maximum of return and the max release of TA minus D, TB, and B, and this. And then we remove the A again. And the best is just the maximum of these two things. In the end, this is what happens. TA should be larger than 0. Yes, it takes 1, and then we do that. We are not summing any negative value or anything, so it would happen that TB is negative because it took, too long to go there. If TA is less than or equal to 0, then we're done. Less than or equal to 1, we could also do this, but that in any case, it will make the output smaller, and we know it needs to be a little bit bigger. So we're not finding the optimal solution, Let's try to find something that is larger than this. So this graph is clearly larger than the other one we have. Could we optimize this code? Further? I guess keeping track of this opened set is one of the slowest things that we can do. Well, today we knew that we were set up for a difficult problem. Okay, 2963. It's not getting better than that. I think I have to leave it here, go grab a coffee, and continue debugging this in a while. I'll be right back. When we don't know how to fix some code, one thing we can do is just refactor, simplify it, and then maybe we can isolate the bug until it is obvious, right? So I'm going to work on the example because it is just faster to run. I would like it to be almost instantaneous to run, but let's see if that is possible. So one thing we could do is we could say the current flow equals, we could increase the current flow by TA minus 1 times the flow of A. So we have the current flow, and this is TA minus D minus 1, sorry. Or let's do what we were doing. Okay. So it takes 1 unit of time to increase it, then we replace the current flow, and we are back on track. So now, again, the red is the maximum of all of this, right? So all the options we have is either this or this. Open.add, open.remove. Another thing we could do, if we wanted to make opened a list, we could just do this plus A, which I think would copy a new opened. Let's see if this would work. It works. It's a bit slower, or maybe not. Maybe it's the same speed. But because why do we need the opened? We need the opened to see that we cannot open it again, right? Oh, sorry, I don't know what I'm doing. So we have the opened to see that we cannot do it again. Is there a better way to do this? Maybe not. Maybe not, maybe yes. We could have a global variable of opened, which is a dictionary of val false for v in graph. If we had this opened, what we could say is if opened, this could even be a set, right? But this would be the same as what we're doing. So if a not in opened, but this is exactly what we're doing before. Open dot add a, open dot remove a. This is exactly the same thing. We're not passing this as a, so I think we can just safely keep it like this because it is shorter. So we are copying this list now. It's maybe a bit slow, but it is clear that when we are adding and removing it, right? So it is also clear now that we could also do this inside here. This would be TA minus 1 times flow of A plus, if we did this, we would have the same solution. And then here, we could just say max of, sorry, but this for blah, blah, blah. So we have this list comprehension. So then return is the max of return and all of this max. If this is the case. If this is the case. So another way to see it maybe is that if A not in opened, we're doing this, TA minus D minus 1, TB, N, which is the neighbor, B, and blah, blah, blah. We're only reducing the time of the A, keeping the B equal, changing the N, and so on. The return is just the maximum of the maximum, so we are, we could say also options, let's call it. So we could either do this max, so move without could either do this or do this. Sorry. We could either do this or do this. The max, blah, 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 right? Let's see what happens here. Let's remove this max. So these are the two things we can do. This is not being indexed because for blah blah blah, this is not parsing correctly. Okay, this is now. Red is the maximum of all of this. Is this right? Oh, no. No, because we're not, we are forgetting the if. So what we have here is that we need to do the maximum of so we could also simplify this. I mean, this is not, I think it is not helping putting this all just in a single list comprehension. It doesn't seem to be happening, to be helping, sorry. So this, okay, this is working. So now we're just doing the maximum of returning this, opening this one A, and so on. We need to think about the algorithm we're following, if it is right. Is it right that we only think of opening something? So is right this memoization part here? Is this correct? Maybe yes, but maybe no. Could we be here with a different number of opened? Could we be here with a different number of open valves? Are all the valves in our input different? It seems like they all are different. 3, 7, 11, 25, 20, 23, 5. They all are different. So that might be helpful. The fact that they are different could also play in our favor. So we could say, are they all different too in the example? Yeah. So let's assert. So if they are all different, one thing that we could do is identify them by the flow, right? So let's assert this here. Assert what? Flow dot values. So the set, the length of the set of flow dot values equals the length of f for flow dot, so f larger than 0 for f in flow dot values, the sum. Is this right? No. Let's print these two values. So what is the length of this set? And what is the sum of, well, but this is not right because plus 0. So this would be 1 plus. Okay, yeah, this is right. So this is working. So what this means is that one thing we could do is if v equals a, instead of v, we could say f. What would happen then? For n in neighbors, so the problem with f, f for n in neighbors of v, but v would be the next, so the first element that has the property, the next v for vf in flow.items if f equals v. Now this code is getting a bit crazy. Okay, so now let's replace it here. So the graph is going to be, so the flow of v for v neighbors in g.items, and the neighbors are going to be a list of flow neighbor distance for nd in ns. What's going on now? AA. Okay, and instead of AA, then we need to choose 0, 0, and 0. Key error 13. Because we're not going to use the flow anymore. We're not going to use the flow anymore. We're going to use the V directly. And we're going to use the A directly. Okay. This is working. What did we gain from this? Well, we simplified this identify valves by their flow. That's what we're going to do here. We're going to generate a graph only valves of flow greater than 0. This is find the distance between two valves, and here we can say that assert that all valves have a different flow or 0. And here we are reading the input. Okay, so this probably didn't help much, but nevertheless we did it. Okay. We're back here, and this problem still needs to solve itself. So TATB, AB, current flow opened. So if the TA is smaller than TB, we move it. So we take the one that has longer waiting time. Then we will move the one that has longer waiting time. Then if this longer waiting time is already less than 0, we return. We could also, no, we need to return the current flow. Then if this ID, so if this element TATB AB, we have seen it before. and what we saw has a larger flow than the current one we have now, we can return it. Here we could return 0 to make it even easier to discard certain parts of the search. Otherwise, we set this maximum flow for this given ID to the current flow. So now we have to move without opening A. We can move to each neighbor of A given a distance of D with D time, so we will lose D time. We move the A, as we said, TP, the new neighbor B, current flow opened, but this is the same. And then we can open the valve A. If we open valve A, then we have TA minus equal 1. This is what we had before. So we can remove this. We'll multiply by A, which is the flow of this element. Okay, I have refactored this a little. Okay. I did something wrong now. Because now I don't know what I did wrong. You see that? Is that the issue? So we had this and now, okay, now. Okay, so this we cannot return 0 here. If we return 0, is that what changes things? Oh no, this is right. So here, okay, no, this is TI minus equal 1. That's what I had to do. So now we got this. Okay, I'm going to run the input one more time, and I am running out of ideas. I'm really running out of ideas. If we are lucky, and we find some the value will be different, but it doesn't seem I'm going to be lucky. So we already tried some value which didn't work. One thing we could do is try to see how far we are. You know, put 70, submit. Too high. Okay. So we got that P2 is less than 2970. So we could do what is called a binary search on the solution, right? We could submit some different values. So we are maybe just one away. Okay, let me see one thing. Are we sure that both the elephant and I start on the same? Would having two of you work together, even if it means having less time, assume that you teach the elephant before opening any valves, giving you both the same full 26 minutes. So the elephant moves to DD. Is there something about the elephant before? One of the elephants apparently figured out how to turn on the distress signal. You need to get the elephants out of there quickly. There's even a valve in the room, and you and the elephants are currently standing in AA. Okay. So the elephant is here. So no valves are open. I think I'm going to submit just 6, 4. So this is not either. There's the subreddit, so maybe I have to wait 5 minutes. I have no idea what the issue is. With the elephant helping, after 26 minutes, the best you could do is 1707. Okay, so I submitted one more solution. I know this is not the right answer. I think I'm pretty sure I saw this, that it's smaller than this, so we're getting close. One idea I had to improve this a little better is to, so we could do the A star thing here. The problem is that if we cut the search, we're just going to get a smaller solution. So I don't understand how we can get a higher solution. I don't understand how we can get a higher solution than this. So and I'm pretty sure the algorithm I got is right. Of course, maybe it's not because I don't have the gold star, right? So if we have seen this, if we have been here before, you know, given this time A, time B, A and B, if we have seen this position before, then, and we got a higher or equal flow than this one, we return 0. Or we return the current flow. So this is the best we can do because we have already computed all of these positions. We could also do this here, you know. Would this change anything? If we compute the return value at the end and we save it, is that saving anything? Oh, that changes something. Imagine if this is the solution. The problem with what I had here is that we're cutting the search early. We're setting a maximum value, but maybe here this is the real maximum value. So here we are saving the value after doing the search, not the one. So here we were saving the max that you could get when you reach somewhere, and here you're getting the max after completing this. So probably, I pray for this to be the solution. So if this is right, then we would have assert P2. I mean, it looks like it. It looks like this could be the solution. 2967. See, we have to wait 1 minute and a half. It looks like we could have a solution. Oh, I'm already thinking of refactoring this code. All of this thing we did of modifying the graph, I think we don't need it. I think it was not such a good idea. The problem takes a bit to run, but it's not terrible. I mean, we could re-implement it in C++ if we wanted, but maybe it's not necessary. It's not necessary. So we have this graph. If distance A, B. You know, I like this walrus operator. So here we could say G A is a list of, well, no, BD for B in G if distance is larger than 0. Is that right? Yeah, that looks fine. And then G, so G is a dictionary of A for A in G. Okay, that's cool. And this V, we probably do not need this, right? So what we are doing here is we are identify the valves with their flow. I think this is something we don't really need. So this is the A, and here when we are summing this is the flow of A, and this is the flow of V. And we got the gold star. Okay, today, I mean, if you see your personal stats, I was faster than most of the people to solve this second part. It took me more than 1 hour and a half, so I'm not in the top 100 for sure, but not bad. Not bad. Better than average. Okay, so we finally got this part. There was a problem with the memoization. So you could see we were we're going to see this later, but we were not doing this right. So this distance, I think computing this distance makes sense. We can remove this. We don't need that. Valve, flow, neighbors, this. Row is this dot split. Just going a bit shorter. So this we read the input. So read the input. Flow, neighbors. We read the input. We calculate the distance between two valves. That is interesting. We generate the graph. So this graph, what does this do? We don't use this, right? Oh no, we use it. Oh, we have an empty list if the flow is larger than 0 and the blah blah blah. So this could be for A and G if flow of A is larger than 0 or V equals AA. Is that right? Okay, G is not defined. For in flow, G is not defined. In flow, V is not defined. Okay. If flow A V. Okay, no. So non-zero valves is V We could also do it like this. Okay. So we could say non-zero. We could say valves equals this. We could replace the G with valves so we don't have this weird, we are reusing the same G variable twice, would be a little bit weird. So here we have the valve and the flow. If there is positive flow, or the AA, which is the start one, then we do this. Max flow best equals 0. So now we need to run part 1. And part 1, we can run this way. Probably we should do the same thing here as we did in the okay. Why curve flow? Why is this not working? This is very... Oh, because we are modifying the T. So we could call it ID equals TV. So if we take the ID and the ID and the ID, wait. Okay, now this is working. So if we take this and put it here, what happens? It doesn't work. Okay, it works. Now it doesn't work. This is undeterministic. So now this is surprising me very much. It surprises me very much that this is undeterministic. Not red, but current flow. If we put it here, okay. It is extremely surprising for me that the first part needs this max flow setting here, and the other one requires it in below. It's very surprising. So here, of course, we can do this for ND in GV. So this is working. We move without opening the valve. Okay, and then we open the valve and visit. So, well, here we could do the same as that we did before in the other part, sorry. So here, instead of a set, this is a list, an empty list. Wait, A is not defined. Well, we call it V here. We could maybe use the same function for both things. We could, but I think we're not going to do it. So release. So here we have the memoization part. LRU. We could use this decorator LRU cache, something like that. But we don't only want to do the cache using this T and V, right? We don't need the other values. So maybe it's fine to keep it this way. If not opened, we remove the T. Global best. Best equals max of red best. Do we need this best? I think we don't need it, right? What do we want it for? In the past, we were using it to do some kind of A star logic, But now we don't need it, so we can remove this. We can remove this. Okay. So maybe I think I know what the problem is. I think I know why this is important. And I think it depends on the graph. So I think the issue is whether in the last minute we're opening something or not. If in the last minute we're opening something, here everything is open. The last minutes. Okay, 81, 81, 81, 81, 81. But here, well, it is also the same, so I'm not sure if that's right what I'm saying. Oh, but the example was working. But in the real input, the problem could be that we are returning, we're improving the return value in the last minute, so we don't, if the improvement is 0, I don't really know what I'm saying. So here we are saving the maximum flow in terms of the result. So if this is not what we should do, if the maximum flow is larger, oh my god, I think this is the issue. We just need to return the maximum flow. We want to return the maximum flow, not the current flow. Print P2. And what we need to assign this is to the current flow. Okay. If this is true, then I understand what is happening. But I'm not sure if this will be true. Then we can get rid of all of this weirdness. Let's see. I'm waiting for the result. It's a bit slower, right? Maybe this is not good. Yeah, this is not good. So if the ID is in max flow, then we return the max flow. But I'm returning 0 because I want to kill this search, right? Let's go to the example because it's faster to run. So now, well, it's faster, but not that fast. So if I go down here and I return the max flow, what happens then? Then we're not killing. Yeah, well, this is working. This is working. So I will print this best. Best equals 0. This was helpful for debugging. If red is greater than best, we have this global best, then best equals red. And we print red. Okay, so this is what happens for the example, but we want it for the input. So for the input, this is clearly slower, but this is probably now exploring the whole search space, which in the past we weren't doing. And the fact that by adding this return after, we got the right solution could be luck. I don't think it's luck, but maybe it is. Maybe it is. So we have the code down here. But that's the logic thing to do, right? If we have been here and this is better, then we need to, okay, 63. This is wrong. So I think it's better to have this 0. Well, let's close this. So it would be better to return 0 and have this down here, and I don't really understand why, but this works. Okay. The current flow, no, we should return 0. I don't even know what I'm doing now. I was removing the best. We have this back. Okay, I'll leave it here. I think I will come back later to refactor this code a little bit. I'm happy that I found these 2 gold stars. It was a difficult problem today. Let me get back later and share my thoughts on how we can improve this code and the lessons we learned. Okay, hello. I'm back. So, after thinking a bit, I think the conclusion I reached is that this solution is wrong. So I think we have reached the correct solution because of good luck, let's say. So here, instead of this, we can assert that the solution is whatever we have in this example. So this is it. And then we're going to assert that part 2 is 1707. Let's run this. And it worked. The problem is that this is wrong. What happens if we return this? Okay, that works. I think the colors got messed up. So okay, now we see this was in gray. Okay, so this is working. And now what we're doing here makes more sense. It would even make more sense if we set this here. But now this is wrong. Why is this wrong? 1, 3. We have different solutions now. So what I'm trying to do is this. Okay. What I would think here is that we are getting this ID, we are computing the solution, and then we're saving this solution here. If we know this solution beforehand, then we return this solution already. The only problem I have, I mean, this is not working. I don't understand why. But one problem we could have is that we would need to have this opened as part of the solution, as part of the ID, sorry. Because we would need to store this ID So it is different. What we have visited in the past makes this different. So what is the problem here? So this is not working. Let me copy this and let's get back to whatever was working now before, and let's paste this here. Okay, this one. Sometimes it works and sometimes it doesn't work. I think I got it to fail. And does this work if we remove this? I guess not. For sure it doesn't. So the question is, have we been in this, given this time, in this valve before? If so, we already know what is the maximum amount that we can release. So let's copy this and have a new one. So this left max release 2, I'm going to call it. I'm going to paste this ID here, and we're going to use a mem dictionary. So if this is in mem, we return the mem. Else, we compute and we save the mem to this value. So now this is working, but we're not using the right one. And this max release 2 should call max release 2 and max release 2. So now this is not working. It has this 1626 solution. So what is the problem here? Here we are really computing for this sorted list of opened. Could we add a comma? I don't know this helps at all. Of course not. So we could here print ID, for example. These are the kind of places that we have already visited, right? So we are at time 25 or having 25 remaining minutes, being at BB, and having already opened these two. But also, we have this current flow. We could also add this as a variable. That's different. Of course, it is too slow because it's not that we have opened all of this, but also when we opened them. So when we opened them is important. Now we got the solution. And now we got the solution. So I think this is right. I think this is the correct solution. And what we had before were just some kind of approximations, let's say. Were just some approximations. But this is the correct way of solving this problem. So I'm going to keep it. I'm going to, even if this is slower, it is clearly slower, but I think this is the right way of doing it. We're exploring, really exploring all of the options. So given this time, this valve, the amount of flow that we have already secured and the list of opened valves. This is the state of this search. If we have seen this search before, we return this. Yes, maybe we could even say TV current flow sort opened. If we are here with the same set of opened, so the only thing I see is that if we this and mem id, so now we would repeat the current flow calculation, but that does not make any sense. So I think this is the correct way of solving this problem. Maybe we could even implement it in C++ later and have it faster. I think there is, we have seen that we got to the right solution quickly by taking some shortcut. So it's not clear that so maybe there is another way, but anyway. So here this is, if this is in mem, then mem return mem id. And here we put, sorry, mem id equals red. So now if we run this, we have to wait a bit. Okay, the assertion failed. What did I do wrong now? Oh, wait. We said this is current flow and comma dot join sorted ordered. So this is the real ID. Now there are a couple of things we could do if this works. Okay, ordered, opened. That's what I meant. So there's one thing we could do, which is re-implement this code in C++. I could do it. I haven't programmed in C++ for some time, so I'm sure it will be, I will not be as fast as I could. But maybe I still got it. Otherwise, if we confirm that we get the solution, we can just be happy, that we found this solution. And that's it. But I think now we are doing the real search. In the past, we got both stars by taking some shortcuts that maybe didn't necessarily cover all of the options. And even when we got the 2 stars, I think there was some randomization in the order in which we visited the neighbors that could play a role in the final outcome. So maybe for some percentage of runs, you would get the right result, and for some other, you would not. So you can see the second part is pretty slow now. If we want to run this search with this in this way, we will need to do it in C++. So we are here. could print G and run this. So for this G, we could simplify this. If we want to read this in C++, what we could do is we could give indices to each of these nodes and then replace this. So we would, one thing we could do is index equals a dictionary of vi for enumerate G, print index, assert false for iv in enumerate G. So we have these indices. So we could do for a neighbors in g.items, or we could do the following. Well, yeah, for v neighbors in g.items, print we could print the length of index to get the number of vertices in this graph, and then we could print a list, the neighbors of each one, which would be a list of pairs, where we have, for nd in neighbors, we would have the index of the neighbor, comma, d. See what we got here. So single, is that? No. Let's just print the index and d. Let's do this differently. Index n d. So we have for each one end equals nothing, print. So we have for each neighbor, okay, and space. So we have node 0 is connected to 1 and 2 with distance 2, 1 with distance 3, 2 with distance 4. This, okay, no. This is the distance to each node. So we do have, of course, this graph is complete. So another thing we could do is for I in range length of index, for j in range length of index, we print the, so what am I trying to do? What I'm trying to do, well, I mean, I think I'm not going to do it, but what I was trying to do is I was trying to print the distances from each valve to each valve, so all of them are connected, apparently. So what we can do, we can just print a grid of the distance from each pair of valves. We identify them by an integer. So let me see, what is the index of AA? Out of curiosity. It's 3. It should be 0. We want it to be 0, right? The easy thing would be to do for I valve in enumerate g.keys print I valve. Let's do this in a different way. Okay, but we could sort this. So sorted this, if we enumerate this in a sorted way, we have these valves 1, 2, 3, 4, 5, 6, 7. No more. So what we could do is, first of all, we print the number of valves. So the length of G, 7 nodes. Then we print for each valve all of its neighbors. So we would, for valve in sorted valve neighbors items valve for neighbor distance in sorted neighbors, print neighbor distance. Okay, so we could print distance, or we could print distance and space print. Okay. So what we have now is the distance from each valve to each of the next valves. So, except for itself. So the distances is a dictionary for ND for ND in this. So now we do for J in, for J underscore, for J V W in enumerate G.keys print distances to W. And this should fail. This should fail because there's a missing key. So we would try this, else except print -1 and equal. So now we should get a diagonal sorted. Okay, it's very stupid what we wanted to do, but now this works. So we have this diagonal of 0 is not connected to 0, and so on. Okay, or we could say 0. So the distance, in fact, is 0, whatever. So now we have the distances of all of these, and we have the flows. So for this same thing here, for I V in enumerate sorted keys, we print flow of V. So A has 0, B has 13, which I guess is right, 220 and so on. So now we have this input, which we can take for to run this program in C++. So C.graph. So let's run this part. Let's try to write this in C++. So we need to include IOStream. We're going to include vector, string, I don't even know, using namespace std to make these things easier, main. So now we're going to read n, and now for in. Now we're going to read the flows. So we could have here of a vector int of flow. Now flow is a vector int of size n. We could have it int n here too. And now we can do for int I equals 0, I less than n, plus plus I. We read flow I. Then the other thing we need to do is have a vector of vectors of integers, which is the distance. And now we will do the same. We're going to have the distances be a vector of integers of size n, and then we're going to the I is going to be a vector of integers of size n, and then we're going to read the I j. Now, the way we're going to handle this is make 16.cc, sorry, make 16, and we run 16 with the 16.graph input. Okay, of course, nothing is written, but if we have this for, well, it is running. I guess this is really being written. So now we have read the distances, we have read this. So now what we want to do is run solve. So we'll do the easy part first or the difficult part first. Let's do the difficult part first. So, or the easy one. Let's go with the easy one. So we have 30 minutes left. We start at position 0. We have 0 length, and we have not seen any we have not opened any valve. So what we're going to do here, we are going to see out this end line. So solve, and we're going to have a map. We'll see this memory later. So what we have is int t, int v, int current flow, int opened. So what we're going to do is, if t less or equal 0, return 0. Then the ID is going to be a tuple of int ID equals make tuple of TV car opened. Now, I don't know how this tuple thing is modern C++. I have no idea how to use it. So we have this tuple. We can have a map from tuple int to an int, which is the mem or mem. So what we're going to do is if mem.find id equals mem.end. So if it is not found, or if it is different than mem.end, then we return the mem id. Now, int return value. So the return value, so for each neighbor, but we're not going to say for int I equals 0. I smaller than n plus I if I different than v, otherwise we don't care. We don't want to go to the same one. We say return value is the max of return value. I think this works. Or let's call it the int new flow is equals to solve. So this is t minus the distance from v to I, then the new I, then the current flow, and the current opened. So if nf is larger than red, red is nf. So this is the first part. Now it's the second part. How do we know if this is opened? Well, we're having to have a mask of bits in opened. So if opened and one shifted v equals 0. So if it is not opened, then we're going to do t minus equal 1, that is minus t. So we decrease the t, and then again we do for int I 0, I minus n plus I, new flow, int new flow equals solve t minus the distance from v to I, the new I, t times the flow of v plus the current flow, and opened or one shifted to I. So we are, no, to v. So we are adding v here. If nf larger than red, red equals nf. And here, the last thing we need to do is mem id equals red, and then we return red. Here you could also do this, I think, but I don't want to. I'm not 100% sure. Okay, let's see what happens if we make this. Okay, map. We need to include a map. This could be an ordered map too. Okay. Okay. Well, this is extremely fast and extremely wrong. Extremely fast and extremely wrong. So, where are we? Could we see out t v current one opened and line? Let's see what happens. Okay, 0, 0, 0, 0, 0. 0 open, 0 current one. This is weird. Okay, let's try to read this code a little bit and see if we got this right. So we are calling this with 30000, which if we vim this, is that what we were doing? 30000. That's what we're doing. We have 0 opened. 30 is the time left. AA we have converted to 0. And so on. So the return value, I don't know if you can do, oh wait, return value is 0 initially. Otherwise, it's just a random value. This is the problem with C++. Problem with C++ and with many others. Okay, if solve is larger than, so we're just returning some kind of random value. So I think we should return the current one somewhere, right? Not 0. Let me vim this. So if time is less than or equal to 0, we return the current one. That's important. Then we make this tuple, return it. So we have this tuple. If find different to the end. So if it is found, then we have this. I think maybe there's some contain or something or some function, but I don't know much. Return is 0. So if I different than v, we solve with t minus the distance, I current flow and opened. And here we do this. T times the flow plus the current one. So here we are adding something. So let's see what's happening. Okay, car is always 0. So let's print this only if car larger than 0. Is this happening? Sorry, we can make 16 and run 16 with 16.graph. This is not happening ever. Okay. Why? Because maybe we are not hitting this if ever. Okay, now we got it. So now there's something. Have to be careful with these operators. So now, what is wrong with this? It is very slow. Mem ID equals return. It is very weird that it is so slow, right? What are we checking? What is going on here? So what are we checking? Sorry, what did I do? Okay. So we are checking many opened, current, 1, 1. So time is 1, v is 1, current, and opened. 74, 78, blah, blah, blah. So it is if we have seen it before, return this value. Otherwise, we run this and then we set this value. I don't know, maybe I should just leave it running for some time. Of course, the Python solution is faster, so there is something wrong here. Here we could say opened or equal 1. That here we can have opened, and we could say current plus equal. Okay, we got the solution. So it does find the solution, but it is a bit slow. One thing we can do, g++ minus o 16.cc minus o3. This is going to make it faster. Of course, there's no need to print so many things. It's weird that I don't understand why this is much slower than the Python one. Doesn't make much sense for it to be slower. Of course, we can prevent this. We can remove this writing of things. Time it. Okay, 2.3 seconds. Okay, so well, we found the solution for the first part. And then we could have the solution for part 2. Let's copy 16.cc to 16-2.cc. And now we will edit 16.py and read the second part. So the difference here is that this is 26 and we have one more 0 and one more 0. So this is TA, TB, int A, int B. That's what we're doing. Here this is have int, 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 TA, TB, AB. That's what we're doing. Current opened, ID. Oh, here we have one more check. If TA is less than TB, we return solve of TB TA BA car opened. Okay, now I want to run it. Now I want to run it. So we have this, then this one, then we check inside with TATB, blah, blah, blah. For its neighbor, we are moving the A. So if, sorry. Yeah, we're moving the A. So for its neighbor, if it's different than A, then this is A, blah, blah, blah. And then this one is the same. Here we have an A and open shift. We do here with A. We have an A. But of course, this is not like this. This is TB, I, B, etc. So now we can make it. Sorry, we want to run the 16.2. Okay, what do we have wrong? Oh, the memory. We need to add a couple integers here because this is now and minus t. That's true. It is TA and t minus 0 is TA and t times flow. Let's find the flow is TA. Okay, now this compiles, not yet. TA, and here we also have the TA. Now we have modified the code for solving the second part. Okay, solve. Oh, wait. This is TA, TB, IB. And now we have it. So now if we run this, oh, it finished too early. It finished too early and with the wrong solution. So we need to check this a little bit more. 26,0,0,0,0. So what is the issue here? TBTABA current opened. So let's check this, the code in Python to compare the second solving function. So first, if TA is less than TB, we do TBTABA current opened. Okay. If TA less than or equal to 0, we return this one. Now we create a tuple with A, B, TATB, AB current opened. We need to remember that we didn't test this problem in Python, so we don't know if this Python solution is right. So then we have return 0. And here for each neighbor different to A, we solve with TA minus D from A to I, TB, I, B current opened. I don't know if you can do this. Red equals max of red and this. Is this something that, you know, is this valid? Is this valid C++? Yeah, it is. So if it is, and we get the same result as before. Yeah. Okay, this simplifies things a little bit. Red equals max red. This simplifies things a little bit. Okay. So if we're here, back here, what we are doing now is, oh, wait. I forgot. Oh, no. The OR is done here. Yeah, we have the OR. So if opened, so if this one is not opened, we can open it, reduce the T, increase the flow, and then for each neighbor, if I different than A, right? I don't know why we didn't have this here. We return the maximum of solving TA minus the distance, TB, I, which here is N, B, the current and opened. Then we set the return value in the memory and we return. Okay, still the same. I think we can also return this if I'm right. Okay, and remember, this is the example. This is the example, I think. I think this is the example. Is this the example or not? So this is, we compile this one and we do the time. Yeah, this is the example. So, well, we got something wrong here. We're not solving the example correctly. And I'm not sure how much more time I want to spend in this problem. We're flipping this. So this is 26, 0, 0, 0, 0, 0. Are we missing 1, 0? Is that possible? So, oh, wait. Oh my god, this is 26, 26. Okay. That's different. That's different. It's taking a lot of time. Surprisingly. But I think we are doing the right thing now. This could all be simplified. All this tuple checking. So the time is always going to be less than 26, right? 26, 26. This is just going to be a small number, and this could be a larger number, the opened. But we could maybe do something like, you know, ID equals, I don't know, something like this shifted 50 or DB shifted 40 or A shifted 30, something like that might help. B shifted 20 or the current one. We might do something like that. Now I don't like that this is taking too long. And we could print cout TA TB A B current one opened and line. Okay, there's some negative things here, which is right as long as we do that, and then the ID, I guess this we are hitting this, right? Print cout. Yes. Yes, yeah, we're hitting this many times. So it's not like we are not using the, it's not like we're not using this. Could we use an ordered map? Instead of is this a different include? What is the problem? Oh, we cannot hash a tuple. We cannot hash a tuple, I guess. So better just use a map. Yeah, but map's a bit slow, right? We have all of these I don't know, this is only the example, so I don't like that this is taking so much when this is only the example. But of course this took a long time also in the Python. I think I'm not sure we were able to get the Python code to run. So maybe this is too slow of a way of checking this. We could also say if I'm wondering if everything is open, then doesn't make any sense to do anything. So maybe we are also having times where everything is opened. Doesn't seem like we do. Trying to squeeze my last neurons to solve this problem. But it is hard. So these were some optimizations. The optimizations we made were just using integers. 1, 2, 3, 4, 5, 6. So we could, let's do this. Int mem. And the ID could be int ID or tuple int ID equals make tuple of. So we're going to multiply this. So 1e8 times ta, 1e6 times tb, 1e4 times a, b, 1e2 times b, and current one. And instead of being this an int, what is this called? Int 64t? What was this called? I can't remember. Let's say long, like old school way of doing this. So if we say this is long, and we comment this line, you can't forget about this. So this is going to be 12, 10, 8, or more than 12, 16, 14, 12, well, not 16, 14, 12, 10, 8. I'm going to sum all of these values. And opened. This is an optimization at the end of the day. But make tuple, line 12, wrong number of template arguments. Find ID, tuple long. So recursion member finding mem, which is of not class type int. Where is the mem? A tuple from long int. Okay, no, it is this to an int. That's what the mem is. Still probably too slow, right? I'll just keep this running a little bit. Compile it with 09. Run it here. Okay, sometime later we can see that we get some result after 8 minutes of wall time. So I'm pretty sure this is the right solution. It will take a long time to run. I'm pretty sure there must be a better way to do this, but we're going to leave it here. This is enough for today. This is enough for today. So we could comment the lessons we learned. First of all, what today proved is that the most important thing in these kind of problems is algorithm is the most important thing. So the algorithm is what covers the complexity of the algorithm is what will rule how long this takes. I'm pretty sure there must be a Python algorithm that is fast enough. The C++ algorithm I coded is slower. I don't know exactly why. Of course, C++ is faster. So the first thing you need to do is you need to think correctly of how to solve your problem. The second thing we learned, well, we used memoization. We used this BFS to calculate the distances. I didn't refactor the code so much today. I'm just too tired. So you can resort to C++ or other faster programming languages if needed. We did it today without great results. I mean, we solved it with Python. Then probably to find a real good solution, we might have need to go to C++. What else did we use here? We used memoization. It's one thing we did. This is usually called dynamic programming. We had this recursive function. So we had a we just did a search on a big space. Really, not many interesting Python features we use today. Mostly we used this was mostly about algorithmics. So I don't think there is much else we can learn from this code with respect to Python. This is one of the days where I think it is more interesting to then go and find the solutions of other people. Maybe Peter Norvig, who publishes his solutions usually in a couple days. It will be good to see how other people were able to solve it, if they were able to solve it in Python, and in how fast or what algorithm they used, and so on. Other than that, I think we can call it a day. Let's see you tomorrow.